Did you know that a single ton of mayonnaise can contain around 650 kilograms of vegetable oil? That's right. And that raises a familiar paradox. We already know oil and water don't mix. So how do they stay suspended together inside a jar of Hellmann's, forming a thick, glossy, uniform cream that remains stable for months? How does a factory force two incompatible liquids to stay together without turning the final product into an oily mess? Today, you're going to discover how everyday ingredients and a seemingly simple recipe are transformed into mayonnaise. And you'll see it all from inside a massive industrial production line. Welcome to Factories and Facts. In today's episode, you'll follow the journey of mayonnaise, from ingredient preparation to the moment the creamy mixture moves through high-precision machinery and into its final packaging. What looks like a simple recipe actually hides a process where temperature, speed, acidity, and mixing order must work in perfect synchronization, like the gears of a Swiss watch. The ingredients seem ordinary: vegetable oil, water, eggs, vinegar, sugar, and salt. The mystery begins when they enter the production line, because that's where science has to prevent the mixture from breaking apart. To make mayonnaise, the oil must be broken into countless tiny droplets and dispersed throughout the water-based portion of the mixture. Those droplets naturally try to merge again, just as oil rises to the surface of a glass of water. The factory must prevent that separation while controlling speed, temperature, proportions, and the exact order in which each ingredient is added. This is where the factory stops looking like an oversized kitchen. Tanks, pumps, mixers, and measuring instruments operate in sequence to create a stable emulsion. Even a slight change in the oil flow or mixing method can alter the viscosity, compromise stability, and cause an entire batch to fall outside the required standard. That's why every step must be precise, repeatable, and continuously monitored. And if you watched our previous episode about ketchup, you saw that the challenge was transforming tomatoes into a thick, uniform sauce. Here, the problem is even more unusual: keeping oil suspended in water as though the two were naturally meant to stay together. And while you're here, check that you're subscribed to Factories and Facts, because now you're about to discover which ingredient truly holds this structure together: the egg, the vinegar, or the sheer power of the machines. The answer begins with the selection of raw ingredients, because before anything is mixed, the factory must make sure every component enters the process under precisely controlled conditions. Before a single drop of oil reaches the mixer, the factory must solve an invisible problem. Ingredients that look identical can behave very differently. A batch of oil that falls outside specifications, a water-based mixture with the wrong acidity, or an ingredient at the wrong temperature can affect thousands of jars. That is why industrial mayonnaise production begins long before the mixing stage. It starts with the approval of every raw ingredient. Vegetable oil, water, eggs, vinegar, sugar, and salt form the foundation of many mayonnaise recipes produced on an industrial scale. The list seems simple, but every ingredient performs a precise function. The oil creates most of the creamy texture. The water forms the phase in which soluble ingredients are distributed. The eggs help bind the oil and water together. Vinegar provides acidity, while sugar and salt balance the final flavor. When these ingredients arrive at the production facility, they do not go directly into the main tank. First, their identity, transportation conditions, integrity, and batch specifications are carefully verified. Samples may be collected to evaluate appearance, aroma, acidity, concentration, and physical behavior. Once tons of ingredients have been combined, correcting a deviation becomes far more difficult. The factory wants to uncover any problem while it can still fit inside a small laboratory container. The oil must be protected from excessive heat, light, and unnecessary exposure to air, all of which can affect its aroma, flavor, and stability. Before use, it may be filtered and carried through sealed pipes to the metering system. Flow meters control exactly how much enters the process, because even a slight change in proportion can alter the firmness of the mayonnaise. It is like building a wall from thousands of microscopic bricks. Too much oil, too little oil, or poorly distributed bricks can reshape the entire structure. Meanwhile, the mixture of water, vinegar, salt, sugar, and other soluble ingredients is prepared separately. The goal is to dissolve and distribute everything evenly before it comes into contact with the oil. The temperature must remain within the range established for the formula because it affects both viscosity and the behavior of the emulsion that is about to form. Sensors track the mixture while agitators keep it moving until it is ready for the next stage. The eggs require special attention. In mayonnaise, compounds found primarily in the yolk act as a microscopic bridge between the water and the oil. This ingredient must also meet strict safety and quality standards. Treated and standardized liquid ingredients make precise dosing easier and reduce variations from one batch to the next. The egg is not added merely for color or flavor. It plays a direct role in the architecture of the sauce. And here is a surprising detail. Before the mayonnaise thickens, nearly everything inside the tank still looks liquid. Its body develops when the oil is broken into droplets so tiny and so numerous that they begin crowding against one another. This only works when the base has been prepared correctly. Otherwise, the mixer can run at full power and still produce an unstable mixture. With the raw ingredients approved, measured, and positioned in their tanks, the factory reaches the decisive moment. Valves open, pumps come to life, and the oil begins flowing at a controlled rate toward the water-based phase. And now, we will see how that stream is shattered into millions of droplets, transforming a collection of liquids into the creamy mayonnaise we recognize. At this stage, an error lasting only a few seconds can compromise the entire batch. Now we reach the heart of the manufacturing process. The water-based mixture is ready, the oil has been measured, and the production lines are prepared. Even so, there is still no guarantee the mixture will work. The challenge is to transform a stream of oil into microscopic droplets and keep them suspended separately throughout the water. To understand what happens next, imagine a crowd trying to squeeze through a narrow doorway all at once. The high-shear mixer forces the oil through a zone of intense turbulence, where the stream is torn apart repeatedly until it breaks into smaller and smaller droplets. In many industrial systems, this action takes place between moving and stationary components, such as a rotor and stator assembly. The rotor spins at high speed, draws the mixture into the mixing head, and propels it through tiny openings. Each pass applies another burst of shear force. Shear is the force that causes layers of liquid to slide past one another at different speeds. In practical terms, it is like grinding away at the stream of oil until it loses its original shape. The more efficiently that stream is broken apart, the finer and more uniform the emulsion becomes. But reducing the size of the droplets solves only half the problem. The moment they form, they begin trying to merge again. When two droplets combine, they create a larger one, and if that continues, the oil may begin to separate. This is the exact moment when the components in the egg go to work. Molecules found in the egg yolk position themselves along the boundary between water and oil. One part interacts more readily with the water-based phase, while the other bonds with the fat. This arrangement forms a protective film around each droplet, making it harder for them to merge again. The transformation does not happen all at once. The oil usually enters at a controlled rate while the mixture circulates through the system. If the flow exceeds the equipment's ability to disperse it, pockets of excess oil begin to form. If the flow is too slow, the process loses efficiency and may drift away from the intended standard. As more droplets fill the tank, the liquid has less room to move. The mixture begins resisting flow, develops body, and shifts from a thin liquid into a creamy texture. In other words, the thickening comes directly from the microscopic organization of the emulsion itself. That is why mayonnaise feels firm inside the jar but spreads easily under the pressure of a spoon. When force is applied, its structure gives way and begins to flow. Once the movement stops, it regains part of its resistance. This behavior helps during filling, transportation, and the final eating experience. Temperature must also be closely monitored because it affects ingredient viscosity and protein behavior. The mechanical action itself can generate heat. Sensors help keep the process within the specified range while the system adjusts circulation, mixing time, and intensity. Another enemy is air. Bubbles can alter appearance, interfere with volume measurements, and create texture defects. That is why some production lines use sealed equipment and controlled conditions designed to limit air from entering the mixture during emulsification. In large-scale facilities, the mixture may circulate through an inline mixer and return to the tank until it reaches the desired standard. In other systems, emulsification takes place directly inside the vessel. The choice depends on production volume, formulation, and the texture the manufacturer wants to achieve. As the process continues, small samples may be tested for viscosity, stability, appearance, and acidity. The factory does not wait until the jar reaches a grocery store to discover a problem. The batch must prove that its structure is correct before it can move on to the next stage. One of the most remarkable details is that two mayonnaises made with similar ingredients can still have very different textures because of droplet size and distribution. The formula matters, but the way the machine transfers energy into the mixture also determines what the consumer feels on the spoon. Once the emulsion reaches the expected consistency, it already resembles the finished product, but it is not ready for store shelves yet. The factory must now confirm that every batch can withstand filling, shipping, and months of storage without losing texture, flavor, or safety. Now, I want to hear from you. Did you ever imagine that the creaminess of mayonnaise depended on controlling invisible droplets? Tell us in the comments what has surprised you most so far, and let us know which city or state you're watching Factories and Facts from. Now, the mayonnaise will face a series of tests and inspections. After that, it will move into machines that fill, seal, and label millions of containers with precision. At this stage, sensors must detect defects the human eye might never notice. When the emulsion leaves the mixer, it already has the right color and creaminess, but it has not yet earned its place inside the jar. First, the batch must prove that it meets the same standard from beginning to end. This is where the factory searches for invisible flaws before they turn into thousands of rejected containers. A sample is sent for analysis of appearance, aroma, flavor, acidity, and texture. The goal is not merely to determine whether the mayonnaise tastes good. It must match the established standard because even a slight difference can be noticed the moment a consumer opens the jar. Texture can be measured with instruments that evaluate how strongly the mayonnaise resists movement. If it is too thin, it may run and appear separated. If it is too thick, pumping and filling become more difficult. The ideal consistency must work both on a spoon and inside the machinery. Acidity is also checked because it affects both flavor and product behavior. The result must remain within the range established by the formula. Samples collected at different points in time help reveal any changes that may occur during production. Another test looks for signs that the emulsion is beginning to separate. The surface cannot release oil, form liquid pockets, or develop an uneven appearance. In the laboratory, the product may be exposed to conditions that accelerate the appearance of defects and help predict how it will behave during storage. Once the batch is approved, the mayonnaise travels through sealed pipes to the filling line. Pumps designed for viscous products move the cream forward without damaging its structure. The flow must remain steady because strong pulses or trapped air can disrupt dosing and leave marks in the texture. Jars or squeeze bottles enter the line and pass through inspection. Containers that are deformed, dirty, or out of position must be removed. Guides and sensors keep every package aligned, creating a formation that resembles an army of containers advancing under a single command. At the filling station, dispensing nozzles move into position above the containers. The machine releases a precise amount of mayonnaise and stops the flow at the calculated instant. Depending on the system, each dose may be controlled by volume, weight, or the exact movement of pistons and pumps. The viscosity makes this stage especially challenging. The mayonnaise cannot splash like water or leave strings that soil the rim of the jar. Nozzle design, filling speed, and flow cutoff must work together to deliver a clean, consistent dose every time. If the rim becomes dirty, the seal may be compromised. Immediately afterward, caps are fed into the system, oriented, and placed onto the containers. Capping equipment applies controlled force, sealing each package without deforming it or leaving a path for air to enter. In some package designs, an inner seal creates an additional barrier. Sensors may confirm that the cap is present, while cameras search for crooked, missing, or improperly positioned components. A tiny failure at this point can undo all the work completed since the ingredients were first prepared. Next comes the weight check. An inline check weigher can inspect every container while it continues moving. Units that fall above or below the accepted range are automatically diverted, allowing dosing errors to be identified without opening jars or stopping the entire line. Labels are applied, and printers add the lot number and expiration date. These codes act as the product's identity record. Inspection systems may perform one final search for irregularities before the containers are grouped and sent to case packing. Approved jars are packed into cases and arranged on pallets. Robots or automated equipment repeat heavy movements with remarkable consistency. Layer by layer, the packages form stable, protected loads ready to move into storage. At this point, the mayonnaise is no longer an emulsion inside a tank. It has become a sealed, labeled, and traceable product. What comes next is just as fascinating: how it moves through distribution centers, which myths surround its shelf life, and why a single jar requires so much engineering before it finally reaches your table. Once packed into cases, the mayonnaise moves into storage and onto distribution centers. Even after it leaves the factory, quality control continues. The cases must be protected from excessive heat, moisture, and impact, while the lot code allows every unit to be traced. During transportation, the goal is to protect the packaging and keep the product within the required conditions. Pallets are arranged to prevent crushing, falls, and deformation. By the time the jars reach grocery stores, they have entered a supply chain that must preserve the same standard created inside the mixing tank. And once the jar leaves the factory, some of the biggest misconceptions about mayonnaise begin. The first appears at picnics and cookouts. Many people blame the dressing whenever food poisoning occurs. But its acidity and pasteurized eggs make commercial mayonnaise less hospitable to many microorganisms than most people realize. That control also helps explain its shelf life. Stability does not depend on preservatives alone. It comes from the combination of acidity, sanitation, pasteurized eggs, droplet size, and sealed packaging. Once open, the product should always be stored according to the instructions on the label. Its appearance reveals another secret. The pale color does not have to come from milk or cream. When the oil is broken into microscopic droplets, they scatter light and make the emulsion appear whiter. Even the color reveals how effectively the machinery performed. That same structure explains why mayonnaise holds the marks of a spoon but begins to flow under pressure. It is what allows the product to be pumped through pipes, dispensed precisely into containers, and remain firmly in place on a sandwich. And that brings us to the strangest detail of all. What looks like one continuous cream is actually a vast crowd of oil droplets prevented from finding one another again. Every spoonful exists because the factory controls a separation that nature is constantly trying to trigger. Now tell us in the comments which discovery changed the way you look at mayonnaise. And to keep exploring processes most people never imagine, subscribe to Factories and Facts and turn on notifications, because the next everyday food may hide an even more surprising feat of engineering. And if you think you've already seen everything, then you have no idea what we revealed in our previous episode. It's already appearing on your screen. Click it, and come with me to uncover another hidden secret here on Factories and Facts. Take care. I'll see you there.